My name is Jonathan Roberts.
I'm David Rowan.
And I'm Greg Richard.
And I'm ENGR, and this is Trust Me, I'm an Engineer. The final step in the Engineering 220 class is to design and fabricate a truss. We then test our truss and analyze the data and ask what we could have done better.
Design objectives. The objective of this assignment was to take everything we had learned thus far and apply that knowledge toward building the strongest and most efficient truss we can.
The material required to build the truss, known as tempered hardboard, is a lightweight composite made from tightly compressed wood fibers. Tempered hardboard has a modulus of elasticity of 700 kSI, a max normal stress of 4060 psi, and a max shear stress of 1600 psi. This material is well known for its unique ability to be both rigid and flexible. The rigidity of the material enables it to hold a heavy load, while its flexibility allows reasonable amount of give, which helps to alleviate stress in the truss. These characteristics in a relatively workable material made tempered hardboard an ideal choice in fabricating our truss.
Here we have our design calculations that we use to efficiently calculate all there is that we need to find on each of the members. We had to find the total force acting on each member, the axial stress happening at each member, figure out which members were in compression and tension, figure out the factor of safety for tensile, figure out the predicted buckling load, and figure out the buckling load factor of safety for each member. So here we have Ian working on a sample of our calculations that we use to find all of our numbers that we put into our Excel spreadsheet.
Predictions. After careful examination, we concluded that the member AG or GH will be the first to fail because they're one of the weakest members that carries the most load. The AG-GH buckling load was 194.8 pounds, and the AG-GH member force was 142.8 pounds.
The actual failure in the truss happened at member BC due to a combination of normal stress and torsional stress. Because the truss was not perfectly symmetrical, it started to twist under heavy load. This caused torsional stress in the members. BC still seems like a reasonable member to fail because it had the second highest torsional stress and second lowest buckling load.
In conclusion, so in hindsight to working on this project, we realized that using X-bracing as opposed to straight across members would have helped to prevent torsional stress being so high. Also, we figured out that if we would have made our truss just a little bit longer instead of the 33 inches that we had, we wouldn't have needed to zip tie our truss down to hold it in place.
For the future of the class, we believe it would be a good idea to move the truss design project back a week. This would make it easier on both the students who normally have finals during the truss due dates and the professors who have to grade finals and truss projects at the same time.